Welcome one and all on this next video related to the unit 3rd, which contain the carbonyl compound as the important chapters. The scope is always same to that this particular pharmaceutical organic chemistry first, then we'll move next towards the important thing, course content. Again same thing is related course content, only this chapter is related with course content, that is the general method of preparation of carbonyl compound and reactions related to this compound, then definition, types, classification, principle, mechanism related to this carbonyl compound. Then important thing related with this compound, that is aldehyde ketone including nucleophilic addition, reaction, electromeric effect, aldol condensation, then crossed aldol condensation, Cannizzarose reaction, crossed Cannizzarose reaction, benzoin condensation, Perkin condensation, qualitative test for the identification of the carbonyl compounds, then structure and uses of the formaldehyde, then paraldehyde, and so many types of the carbonyl compound. Then we will move towards what it include. It include introduction of carbonyl compound, structure of carbonyl compound, nomenclature of carbonyl compound, their isomerism, then method of preparation of carbonyl compounds, physical properties of carbonyl compound, chemical properties of the carbonyl compound, then qualitative test for carbonyl compound, and lastly the structure and uses of that various compound including your syllabus. Then introduction. Let us start with the introduction of the carbonyl compound. So the aldehyde and ketones are the classes of the compound, both of which contain a carbon doubly bonded to oxygen. So carbon is doubly bonded to the oxygen. This C double bond O is called as a carbon oxygen double bond, nothing but the carbonyl carbon. So C double bond containing compound is the carbonyl carbon. It may be aldehyde or it may be ketones. So the group C double bond O known as a carbonyl group, and that is determines the chemistry of the aldehyde and ketone, and hence these compounds are collectively called as a carbonyl compound. Why it is called as carbonyl? Because ketone and aldehyde contain C double bond A as a determining functionality. So in aldehyde and aldehydes, carbonyl linked into the one hydrogen atom. Here the aldehyde carbonyl group containing carbon is attached or linked to this one carbon atom and one alkyl group. While in case of the ketone, carbonyl group is linked with the two types of the two alkyl groups here. Then these ketones are called as symmetrical ketones or asymmetrical ketones. So according to two types of the alkyl groups present on the carbonyl carbon. If it is same alkyl group present on carbonyl carbon, it is symmetrical. If two different alkyl group present on carbonyl carbon, it becomes asymmetrical. For example, it is CH3 or it may be C2H5. So it becomes asymmetrical. The functional group characteristic of aldehyde and ketones are respectively, this functional group is nothing but C double bond O H, nothing but aldehyde, and C double bond O only, it becomes ketonic. So these are the ketonic, this is of ketonic functionality and this is of aldehydic functionality. The next, orbital structure. So it is very simple orbital structure as that of your alkene, double bond C double bond C, or that of C double bond O or C double bond C. So the carbon oxygen double bond in aldehyde and the ketones can be formulated in a manner similar manner to that of carbon-carbon double bond in alkene. So here we assume that both carbon and oxygen of the carbonyl group are in sp2 hybridized form. So one sp2 hybridized orbital of carbon overlap with the another sp2 hybridized orbital of the oxygen and forms alpha bond, while the residual p orbital, so remaining p orbitals, forms the pi bond, overlap with each other and forms pi bond. So one gives a single sigma bond and other gives the overlapping pi bond. So therefore the carbonyl bond, double bond, is in fact made up of the alpha and one pi bond. So here is we see. So R C C, in this case both of the carbon as that of our alkene. So we get the overlapping here by remaining residual p orbital and forms a double bond pi bond. So pp orbital as same as that of your alkene. Here is a oxygen having residual p orbitals. So first sp2 hybridization forms sigma bond. Here is a sigma bond, and sp after this remaining p orbital forms a double bond here. So pi bond forms. So it forms a displaced pi cloud. So this is the same as that of your alkene. Then it may be noted that in the above model of the carbonyl compound, all the three sp3 orbitals of the carbon are in forms a sigma bond. Means we form, here is a one sigma bond, here is a one sigma bond, and here is one sigma bond. So it will totally form 3 sigma bond in sp2 hybridizer orbital. And on the other hand, one sp2 hybridized orbital of oxygen forms a sigma bond, and 2 unused ones are occupied by the pair of the electrons. So why? So there is one is pi electron and one is the, here is the pi bond and here is the pi sigma bond. So also since the electronegativity of the oxygen is higher than that of the carbon, electronegativity of oxygen is higher than that of carbon. So pi electron cloud displaced towards the oxygen and shown in above model, and this causes net polarization of the bond. So carbon becomes slightly positive, carbon becomes slightly partially positive, and oxygen becomes slightly negative, forms the delta positive and delta negative charge on. So thus the carbon double bond can be represented as here pi bond and as here sigma bond. So the carbonyl double bond thus differ from the carbon-carbon double bond of the alkanes, and which is a non-polar image. So the above structure of the carbonyl compound accounts for their higher dipole moment because it forms 2.3 to 2.8. The electron diffraction and spectroscopic studies reveals that the carbon, oxygen and other two atoms or the group attached to the carbonyl carbon lies in the same plane and have the bond angle become, so it becomes 120 degree. So each and every where the bond angle becomes same. So that fact supported that formulation of structure of aldehyde and ketone are described above. Then nomenclature. So aldehyde is a common name of the aldehyde are derived from those of the carboxylic acid to which they are oxidized. So common aldehyde and carboxylic. So we differentiate this by one of the reaction, that is oxidation of the carboxylic acid. So the portion acetic acid, so ICIACID, we can replace name of the corresponding acid replaced by the suffix aldehyde. So it become acetaldehyde. So replacement ICAID is taken. So CHCCHO is oxidized to acetic acid, is named as the acetaldehyde. So in this is of example representation for the naming of this acetaldehyde. In the IUPAC system, aldehyde are named as a alkanal, and the name of this individual aldehyde is obtained dropping the terminal E. So we want to drop terminal E of this methane, and addition of Al is taken as suffix. So it becomes the name of HCHO, that is methane is converted into that is methanol. Then there are different examples, that is HCHO formaldehyde, common name, IUPAC name becomes methanol, and so on. Acetaldehyde becomes ethanol, propanaldehyde becomes propanol, butanaldehyde gives butanol, and acrolein, common name system, becomes propanol. So while the assuming IUPAC name To the complex aldehyde, the longest chain including CHO is selected first of all, and it is numbered from the carbon of the CHO. The assigned is number 1. So a substituent on this chain are given the positional number and name is the usual fashion. So aldehyde group CH always at the end of the chain and is necessary to specify the systematic name. So it becomes at the 3 positions 3 CA methyl group, so 3 methyl butanol. So longest chain is butane and at the first position is CHOs. And there is another example 2 ethyl 3 methyl methyl pentanol. Then ketones. According to the common name system, symmetrical ketones are named dialkyl ketone. Dialkyl ketone. First name members of this is CH3 C double bond O CH3 is however properly called as acetone. So common name system of the unsymmetrical ketone are obtained by naming the alkyl group are separated two words in alphabetic order and adding the third word, that is ketone. So and only add the ONE. So in that IUPAC name of the ketone always alkene on and the name of the individual member system dropping the E of this presented hydrocarbons and adding the suffix ONE. So dropping E, adding ONE. So it becomes acetone becomes propanone, then ethyl methyl ketone becomes butane. So common system, and this is a few ketones given in this fashion. Then while the naming of a higher ketones IUPAC system becomes, we select the longest chain. Then if there is example 2 pentanone, then 2 positions C double bond O. In complex compound refixing position of number of the ketone given the confusion in interested because the suffix ONE. So becomes 4 pentene 2 on 4 pentene, there is a double bond and 2 position C double bond O. So for naming the compound which is addition of the carbonyl containing another group, term OXO is oxo is used to indicate the position of the carbonyl on the hydrocarbon chain. So 3 oxo, so 4 methyl 3 oxo 1 pentanol, as like this. So because OH group is there. So similarly, sometime while naming the substituent ketone, the position of the side chain of the substitute ketone, Greek word we can use alpha, beta, gamma. So carbon adjacent to the is called as next to it beta. So because here is alpha, it is carbonyl carbon. Here is a neighboring carbon called as alpha dash. Here is the next carbon becomes beta. So alpha chlorobutanone, alpha dash dihydropropanone, as like this. So